B, part 6, Exterior Algebra. Okay. Now, lecture 2, Tensor and Covectors. The operator D. This operator is quite important and plays an important role in the exterior algebra. Now, recall that this is a vector space V. You see, these are the bases, okay? In this case, the covariant bases. And this V star is in this case, is the dual space or covector space. dx1, dx2, dxm, they are the co-bases, let's call this, of this space, the dual space V star. So the covector that operates on this, the basis partial of xi, according to the dual basis, the definition of this, you see, definition here, this is, we derived, you see this definition on the previous lecture, so this is the Cronach delta. Hence, dxi at p, I is equal 1 to m, this forms a basis for the cotangent space T asterisk m. Hence, let's say omega p is a covector, okay? This omega p is a covector omega. Yp, you see, I can expand Yp in terms of the cotangent space, cotangent basis. See, this dxi of p, where this is a vector, okay? This is one omega p partial xj is omega I dxi of p. Now I multiply both sides by partial or partial xj. You see, both sides. This is, let's show clearly, this omega p, this omega p. So I multiply these by partial xj. Now apply the definition, okay? Cronach delta, dxp I dxj is delta ij, so this is omega j. These are the components of this case of the covector, okay, expressed in this base here, okay. This base here belongs to the cotangent space, and you see the index here, which implies that dxp at I is the contravariant, okay, basis, okay, and the components are in this case covariant components and contravariant basis. It's clear this. Now let's move to step 1. A function f maps a point of m to the real R, okay, the real number, okay. This is a zero form. This is a zero form, okay. Numbers, functions are zero form. It's assigned a real number to each point on the manifold. You see, that's what this function does. So a zero form is just a smooth function, f, that belongs to the zero form here, that belongs to m. This is a function, this is c infinity of m, which represents a smooth, okay, a smooth function, c infinity of m. So the first, the second, and the nth infinity derivative, they are smooth. So f at p belongs to R. You see, because it maps a point on manifold to the real number. You see, for each p belongs to m. Intuition. A zero form contains no direction informations. See, this is step 2. The differential df is a one form. Why? You see, if you expand the f here, is a function of x1, x2, and so on to xm. This is the f is partial f with respect to xi, dxi. You see, this here is the basis, okay? The base that belongs to the cotangent space. Don't forget that. So these are scalar, numbers, or see this is a vector. See, this case is a vector that belongs to the cotangent space. Look how interesting. F is a zero form. df is a vector which is one form. You see, instead of say vector, say one form. So d here increased by one this form here. So d increased the zero form to one form. You see, so vector, this case, covector are called one form. The scalar is zero form. The operator d, okay, transform zero form to one form. This is the key idea. The maps f is scalar, attention now, zero form to the f, which is form 1. This is the exterior derivation, the derivative d, you see? So d is an operator that increases by 1 the form. You see next lecture, you see, when you have a k form, d applied to a k form, this leads to k plus 1. You see, that's a very interesting property. And also, we will see later, okay, in another lectures, that d squared is equal to 0. You will see that. So, this, I repeat what I said over here, d, okay, maps the a scalar, okay, the zero form maps to one form. df belongs to the one form. dfp, you see, acts on TPM and leads to a real number. So this is important because this at each point P of the manifold. So at this point P, the differential df acts on the tangent vector. You see, xp belongs to TPM. This is a tangent vector, the flow. You see, as we derive in part 5. On part 5, we derive what is this tangent vector here, xp. So dxp acting on dfp acting on this tangent vector here, this by definition is the tangent vector act on f. So it is equal to direction derivative of f along x. See? Now, this definition makes clear that, you see, the definition over here makes clear. df is a map from vector field to smooth functions, as you see over here. You see? It's a linear and satisfies the Leibniz rule. Leibniz rule or product rule, okay, it's the same. And therefore, in this case, it qualifies as one form. So df is qualified as one form. If f is zero form, f is a function. Now, next lecture 3, I will present a numerical example, okay, just to verify this relation over here. You see? This relation over here. You see this, I'll give a clearly one example, numerical example, just to see that relation over there. That's it. That's lecture 2. Now, next lecture 3, okay, I will show an example just to to get that definition. Okay, that's it.